Okay, here on section 3.2, we're going to start plotting points and also plotting linear equations. First of all, let's go over plotting points. On this, we have some x values. That's the your PO2 level. And over here is your percent saturation of hemoglobin, and that's going to be your y values. So here's your x values, and here's your y values, and each pair of these makes a coordinate. So, like for example, this 20, 35 is a point that we're going to plot, and then the 40, 75 is a point we're going to plot, and so on. So we should end up with 5 points here. So we're going to graph these on an x and y axis. This x-axis is your horizontal axis, and that's going to stand for the percent saturation of hemoglobin on this problem. And this vertical axis is your y-axis, and that's going to be your PO2 level. Now, hopefully you already have your book so that you can follow along with this, and we need to plot these points. So let's go ahead and do that. I have my axis drawn here, and the first point I need to plot is the point 20, 35. Well, I'm looking at my x values, and they go 20, 40, 60, 80, 100. So I can go ahead and make each hash mark here worth 20, like 20, 40, 60, 80, 100, or you could scale by tens if you like. And then the y values, they basically go up to 100 too, so I'm going to do about the same thing here. Let's do 20, 40, 60, 80, and 100. Now if I had negative x values, I'd go over here to the left. This would be the point 0, 0 right here. This has a x of 0 and a y value of 0. But I could go to the left and negative 20, negative 40, and so on. A lot of people might label these 1, 2, 3, and so on if you're dealing with smaller numbers. That's just the scale of your graph, how much each little hash mark is worth. And also the scale of your x and y axis doesn't have to be the same. So this would be your negative y values here, and you can just continue this on as far as you need to go. The axis goes forever on both directions. Same way this right here, the y-axis, has positive values going up and negative values going down. Negative 20, negative 40. Now we don't need those on this particular problem. So let's go ahead and plot. The first point is at the point 20, 35. I'll just write the coordinate in here somewhere. Let me write it over here. 20, comma, 35. Okay, so I go to the right 20, then I'm going to go up to 35. Well, here's 20, here's 40, so 30 is about halfway in between. So 35 would be a little closer to the 40, so we're just estimating it here. So about here is the point 20, 35. The next point we're supposed to plot is a point 40, 75. So go over to 40 and go up to approximately 75, which will put you somewhere about here. Then the next point is the point 60, 90. So go out to 60, go up to 90. And some people are really used to plotting straight lines, but not everything is a straight line. As you'll see here, the next point is 80, 95. Well, 80, 95 would just barely, it's the same amount over to the right, 20, but it's barely even higher than the last point. Maybe about here, and the last point, 198. 100 on the x-axis, 98 on the y-axis. Now we're supposed to draw a smooth curve through these points. So I get something like this. And probably you might get the idea that this function pretty much levels off at about 100% right here. And then probably backs on down like this if we would extrapolate, which means predict outside the range of the data points. Probably go something like that. Has some questions here at the bottom of the page, and those questions are, well, we drew the smooth curve, and it says use your curve to estimate the percent saturation of hemoglobin when the PO2, that's your x value, is 35. Well, let's do that. When the x value is 35, what's your PO2 level? Well, here's 35, go up, oh, I don't know, maybe it's around 40 something. And the next problem says use your curve to estimate the PO2 level. That's what your x-axis stands for, the PO2 level. When the percent saturation of hemoglobin, that's your y-axis, is at 60%. So when this is at 60%, this is going up in percentages here, 60%. What is your PO2 level? So I'll go up here to 60. I go across till I hit the curve, and I see that that's, you know, pretty close to 40 right there. And next question says, does the percent saturation of hemoglobin increase more when the PO2 level goes from 0 to 40? Well, going from 0 to 40, it increased from 0 up to about 65 or so. And then, when it goes from 40 to 100. Well, when it goes from 40 to 100, I know the PO2 level has increased a lot, but your height of this thing, which is your percent saturation of hemoglobin, hasn't gone up very much. It's gone from about 65 to 90 some, so that's only a difference of 30. So you've got more rapid increase from 0 to 40 than you do here, where it's starting to slow up in terms of its growth. So we'll hold up there, and we'll do the next example. Okay, this next problem wants us to graph the relationship between the amount of time that a person has been experiencing hyperthermia and their actual body temperature here, their Fahrenheit temperature. So this is going to be the x-axis, is going to be the amount of time that's gone by in minutes. And here is the person's body temperature, that's going to be the y value. So we need to plot these points. Let's go ahead and do that. I'm looking on the x values, and they're just 0, 5, and 10. So we could just do that. We could just say, okay, out here somewhere is 5, and out here is 10. This would be an x value of 0 here. And then our first point is about 98.6. Well, instead of going 10, 20, 30, 40, 50, 60, 70, 80, 90, and having all of our graphs squished up here, I'm looking at my y values, my Fahrenheit temperature, and they're all squished in there between 98.6 and 102.1. So I'm just going to say that we're going to skip these numbers up to that 98. So some people put a little break in the graph here, something like that, but really what matters is that we can see this graph good. So 98, 99, 100, 101, 102, and that should pretty much do it. I don't think we have anything as high as a 103. And this x-axis again stands for time on this particular problem, and you'll find that a lot of problems as you go through your math courses use time as the x-axis. So this is the time variable right here, and this y-axis is your Fahrenheit temperature, your body temperature. And what's going on is the first point is at 0, 98.6. So here is 0 on the time axis. At time 0, their temperature was 98.6. Well, see, now we can have a lot of room in between 98 and 99, and 0.6 is a little bit more than halfway, so there'll be a point right about there. In 5 minutes, their temperature was 100.5. So their temperature is rapidly increasing. That's hyperthermia there. So I went over 5, and I went up to a height of 100.5. And then the next point is at 10 on the x-axis, 10 minutes, and their temperature was 102.1. Well, that'd be right about here. And if I draw a line through this, it would look pretty much like a line. Maybe not exactly, but something like that. And again, I'm just roughing in the graph, and sorry about my bad artwork, but a graph, that's the points plotted, and probably it would be about a line that would go through that. This axis here it's the x-axis. It's for this particular problem, it's time, and it's also referred to as the independent axis. And this is the y-axis on this problem stood for Fahrenheit, and it's also known as the dependent variable. So when we're graphing points in the next video, if we're graphing something like y equals 2x plus 3, the y is going to be this vertical axis right here, and your x is going to be the horizontal axis. And you can see that your y value, Your y value here is dependent upon the number that you put in for x. You can put any number in for x. It's independent. Your y is dependent upon the number that you put in for x. So that's why people refer to the y-axis as the dependent variable, and the x-axis is where you put your independent variable. And we'll stop this video there, and we'll start plotting lines on the next, and graphing lines on the next video.